Okay, conduction, convection, radiation. First one. So I will revise through with you some of the things that the key important points for these two parts, especially for your extra notes given by your teacher. So first is conduction. Now, conduction is all three is the mode of three ways of heat transfer. There are many ways where heat can flow from one place to another place. Okay, first thing, heat will flow from one place to another place. Why does heat flow? Still remember? Why does heat flow? Heat flow because there is a difference in temperature. Okay, if temperature is the same, then heat will not flow. Okay, it's incorrect to say heat will not flow. Actually, it will flow, but there is no net heat flow. If you have like two objects having the same temperature in contact, then the net heat flow is 0. Okay, so if the temperature, one is higher, one is lower, then there is a heat flow from the hotter one to the cooler one. So heat will flow, and why it flows is because there's a difference in temperature. That's it. Here we talk about the ways where heat can flow. There are three modes of transfer of heat. The first one is conduction. Conduction basically is the heat transfer in solid. Okay, just put it simply, solid. You hold the cooking pot over the flame. After a few seconds, you can no longer hold the handle anymore. If the handle was made of metal, let's say, if the handle was made of metal, so you hold it over the flame, after a few seconds, it becomes very hot. So the heat transfer from the flame to the bottom of the pot, and then it goes to the handle. Okay, so this transfer is through the medium. The medium is the pot. Okay, the solid material. So the medium is solid, right? So heat flows using the solid as the medium of transfer. We call it conductions. Okay, so to put it simply, it is the conduction happen in solid. Now, not just solid. It can be solid to gases. Sorry, let me rephrase. It can be solid to liquid. For example, like your electric kettle, the heating coil at the bottom of the electric kettle, it is in contact with the water surrounding it. Okay, so that is also conduction. The heat from the coil transfer to the water. That is also conduction. Okay, so it can be normally it occurs in solid or solid to liquid. All right, solid to liquid or liquid to solid. That is conduction. Now, what are the key words for conduction? How do you define it? Is you mentioned about no movement. Wait, let me use the drawing tools in the PowerPoint. This one. Okay, because I tried before, if I use the drawing tools from the Zoom, something's wrong. I cannot erase it later. Okay, you should be able to see why is it so lag? Wait. Give me a second. Okay. Cannot press this. For some reason, I cannot press the drawing tools at the bottom. Oh, okay. Okay, I stopped sharing first. Something's wrong with the tools. Sorry, let me test a bit. This one. Okay, I try again. Okay, let me try and use the drawing tools inside. Okay, you should be able to see my drawing tools. And okay, yeah, I have to press the ESC. Okay, too long I didn't use the PowerPoint. Okay, now let's continue. So first is, you mentioned about there is no movement of particles. Meaning that in conduction, particles cannot move. Just like in solid, the particle in solid, it stays fixed position. They cannot move as in like they travel from one location to another location, but they can vibrate. They can vibrate. So what happens is that when you hit the solid metal, particle vibrates because heat is just vibrational energy. Remember in the heat chapter, if something has heat, they vibrate to a certain degree. If they do not vibrate, right, stays like just at rest, completely stop, that means that is absolute zero, no more heat inside. So any object that has heat, they have certain degree of vibration. The more the vibration, the higher the heat, the higher the energy. So heat is just vibrational energy. Vibrational energy. Okay, so what happens when one atom vibrates, causes the second atom to vibrate as well. Because of what? Because of the bonding of it. The intermolecular forces between the two atoms, when one excited, it excites another one. Okay, when you get excited, you excite your friend as well, right? So slowly every single particle vibrate, and that is how the heat is passed from one atom to another atom. Okay, so atom at the left causes atom at the right to vibrate after a certain period of time. So that is the first method of transfer in conduction. That is through the vibration of particles. Vibration of particles. There is another one. Second one is on top of the vibration of particles, there is free electron also help in the transfer of the heat. So, but this one only happen in metal because only metal has free electrons. Okay, let's understand what is free electrons. Free electrons, for example, you have the lattice structure, right? This is the structure of the atom. Electron is bounded in the atom, right? It is held by the nucleus of the atom. So if I just pick one atom, you have the nucleus, and then you have the electron, okay, orbiting around it. So the nucleus prevents the electron from going up. What is the job of an electron? What is the job of the electron? They have only one job, is to do the valence pairing. Okay, their job is to do the valence pairing. So they pair with another electron to achieve this stable electron arrangement. Now, these are for all the valence electrons. The electrons that are stuck inside the atom, they are forced to do this job. Okay, they are forced to do this job. Now, when the electron gain enough energy, what happened to the electron? They can actually go out. Okay, they can go out of the atom. They can leave the atom. Okay, now when I say they leave the atom, right, they are not leaving like entirely. They come up from to the atmosphere. No, Okay, they just leave the atom, just leave the one atom, okay, and then they go out like here, they go out here. They become free from the atom and they go to the structure like this. This is the lattice structure of the metal. Okay, and then they are now free to move everywhere. Okay, anywhere they want. They can move around, they move in random direction at very, very high speed. Okay, at very, very high speed. They got nothing to do. All these free electrons got nothing to do already. Okay, they're already free from their valence job and they got nothing to do. Just move around. Okay, so these are the free electrons. So if you're talking about electrons, is it being emitted out? No, it's not being emitted out. It's still inside the metal, just that they are free from the single atom. Okay, the single atom, free from the atom. All right, so all these free electrons, they wander around. When you hit the material, okay, you hit one side, hit here. All the atom vibrate, right? Vibrate, it causes the second one vibrate also. What happened to the electron? The electron also carries the energy. But the thing is that the electron are free to move, right? They're free to move. So they can get the energy, they carry the energy, and then they move across the structure. Okay? They move across the structure, carrying the heat energy with them. So this is like one additional layer, one additional method of transferring the heat. On top of the vibration of the particle, the electron actually speed up the heat transfer. Okay, it speed up the heat transfer because the electron can move. It's way faster, the transfer of heat. And this only happens in metal. Okay, non-metal, they do not have free electrons. So that is why non-metal, generally, they are not a good conductor. Okay, not as good as metal. Okay, so that is heat transfer via conductions. Okay, so here you look at the diagram, we have 3 rod metal, okay, copper, iron, metal, and glass. Glass is not metal. Right, so you dip this 3 rod to wax, and then you do a simple experiment. You hit one end and observe which one melt first. Okay, so you find that okay, copper is a very good conductor. So last one is glass, because glass is an insulator. Okay, so maybe they'll ask you to describe. Okay, design an experiment of see whether copper is a good conductor or steel is a good conductor. Which one is a better conductor? Okay, so you can sketch this diagram, this experiment, it's a simple experiment to find out which one is a better conductor. Okay, so that's for conduction. Next one. Okay. Okay, next one is convection. Convection happens in fluids, so medium that can move. Medium where the particle on top and the bottom. Okay, something's wrong here again. Your microphone and speaker are not working properly. No audio will be recorded. Okay, check if you can hear me. Type yes in the chat. You can hear me. Type yes in the chat. Okay, thank you. Okay, the audio, no problem. If suddenly you hear no audio, let me know. Okay, I see a pop-up here. It says that my audio it's not recording my audio. Okay, never mind, we continue. Let me know on your end if anything happens. So stop me anytime. Right. So we draw an imaginary line here, separate the two regions of water. If I hit the bottom, then I get warmer liquid and cooler liquid on top. What happened to the heated water? When you heat the water, particles, they expand. Here we have 4 particles. When they expand, meaning that they move away from each other. They acquire more volume. If you calculate the volume, maybe the volume enclosed by the 4 particles is V1. When you hit it, they move further apart. And now the volume acquired by this same amount of particle become bigger, V2. V2, okay? When they expand, doesn't mean that the particle become bigger. They just move further. So they acquire more volume, but you have the same mass the same, mass the same number of particle. So density equals to mass over volume. When the volume become bigger, density will decrease. So heated water has a lower density. So if it has a lower density, then it will rise because low density is lighter. Okay, it will rise up. And conversely, the cold water, which has got a higher density, it will come down. So they both switch direction, switch position. Okay, so as a result, you get this kind of movement. When the hot liquid comes up, it creates something like a vacant space. Okay, vacant space where there is a partial vacuum, something like that. Okay, partial vacuum, and then quickly the cold water will fill in. Okay, it will fill in. So this movement is caused by the denser liquid fill in the gap, filling the gap. Okay. Right. So what we have here, when the region of the fluid is heated, the particle move faster and spread apart. The volume of this region increases, but the mass of the particle remain constant. Okay, this is the explanation. If they ask you, why does hot air rises, cold air sinks? This is the explanation. Okay, you talk about the density. So the density of the region of the cooler fluid now become higher than that of the heated region. Hence, hot fluid rises and cold fluid sinks. This is a general rule of thumb. Hot fluid or hot gases always rises, cold one always sinks. Okay, and then it sets up a convection current. How do you prove this one? Okay, how to prove that the convection current happens? You can put impurities in the water. Okay, you can put impurities, a crystal, blue crystal, anything. Okay, and then you observe the motion of the crystal inside. Okay, it goes like in a circular motion, right? Or you can put like in your note, it says about like potassium manganate, right? So it diffuses into the liquid to prove that the distribution is even, okay, throughout every part of the liquids. Convection in gases. Okay. A box with 2 chimneys is used. Candle is placed under one of the chimney. So this is to heat up the gas. So here I draw a line again. I draw a line, vertical line. We have warm air on the left, and we have cooler air. The smoke is just to show the trace. Okay, just to show where is the air moving, to show the traces. Because without the smoke, you cannot see. So we take a smoldering paper, and then the smoke will go in this direction. Okay, why? Because the candle, first it heats up the air above it, right? This region of air become warm, density decreases, so it rises up. Okay, the hot air rises, and then again, it creates a partial vacuum. The cold air quickly fills in the gap. Okay, so you get this movement from here to here. Okay, you can see from the smoke, the traces of the smoke. Okay, so explanation on the right. Air above the lit candle is heated and expand. As a result, its density decreases and rises out of the chimney. The cooler surrounding air is denser at the other chimney, representing by the smoke. So it sinks through and to replace the hot air. So convection in gases and convection in liquid. Now, another example, you can think of it like how the air inside a car is heated up. It's like you park your car under the sun for a few hours, right? Then the air, when you open the door, is very hot inside, right? So how the gases inside is heated up is also through convection. Okay, it's also through convection, but not as significant. Okay, because of the volume inside is very small, just a small volume. But the gas inside is also heated up through convection. Okay, first is the sunlight heats up the car through radiation. Okay, because it's radiation is through vacuum. We'll come to that later. So radiation heat up the car, and then how the gases inside the car is heated up is through convection. Okay, that is also another example of convection. Okay, next one. Application of convections. Okay, so the first one I mentioned just now, and also the heating element of a electric kettle. Why the heating element is placed at the bottom and not on top? Similar reason to why the aircon is placed on top and not the bottom. Again, it's due to the same reason, the convection current. Here, I place at the bottom because I want to create warm liquid at the bottom and cooler liquid on top, so that warm liquid can rise and the cold liquid can sink. And this circular motion ensure the heating is even. Okay, the circular motion ensure the heating is even. The heat is distributed to all parts of the liquid. So if your heating element put on top, then you get warm liquid on top and cold liquid at the bottom. When that happens, the warm air stays on top. Sorry, the warm liquid stays on top and the cold liquid stays at the bottom. Okay, so the warm liquid cannot come down. It's because it's already, initially it is at the top and it's less dense, right? So it stays on top. There's no convection current, no movement. So you get, after a few minutes, you get hot water on top and then the bottom region is cool. Okay, the heating element is placed at the bottom of a kettle. So when electricity is turned on, heating element heats up water at the bottom. Hot water rises and cold water sinks. Convection current is set up and water in the kettle is heated up more uniformly and effectively. Next. Aircon. Okay, it's placed at the top of the wall because you want to cool the air on top first. Draw a line, imaginary line, you get cooler air on top, and then you get warmer air at the bottom. Cold air, denser, sink down. Warm air rises. Most of the objects are placed closer to the ground. So the air closer to the ground are warmer than the air above. Because every object, they give out certain degree of radiation. Okay, even human body give out radiation, meaning that human body from time to time, it gives out heat energy. Every object around you, okay, they give out certain amount of heat energy. So the air closer to the ground is always warmer than the air above. Warm air rises, cold air sinks. Again, you have a convection current. The room is cooled uniformly. Sea breeze and land breeze. In daylight, the land is heated up faster than the sea. Why? You can already answer this because you have learned specific heat capacity. What is specific heat capacity of the sea, of water? 4200 joule per kg per degree Celsius. Land, okay, let's take an example of sand. Sand, okay, about 800 joule kg degree minus 1. It takes 4,200 joule to increase by 1 degree. So which temperature will rise faster? Land will rise faster. Okay, so in the day, the land gets heated up faster than the sea. So the air above the land also will be warmer than the air above the sea. Warm air rises, cold air fills in. Yeah. Okay, so you get the wind blowing from the sea towards the land. So the cooler and denser air from the sea flows in to replace the rising hot air. The movement of air from the sea is called sea breeze. Land breeze, you take the reverse. In the night, which one loses heat much faster? The land loses heat much faster than the sea because it has lower specific heat capacity. Okay, release 800 joules, already dropped 1 degree. The sea has to release 4,200 joules of heat, only drop 1 degree. Okay, so this one, the land loses heat much faster. Temperature drops faster. So what happened? The air above the land, cooler, it cools down faster, right? It cools down faster because the release of heat is faster. So the air above the sea cools down slower. So you get warm air here. Warm air rises, cold air fills in the gap. So you get wind blowing from the land towards the sea. If you happen to live near the sea, in the night, observe where is the wind movement flowing. Okay, it's from the shore towards the sea. So these are a few applications of convection. So again, what is convection? It is the transfer of heat with the movement. You have to talk about the keyword, movement of particle. Movement of particle. Why it only happens in fluids? Because only fluids particle can move, solid cannot move. So it only happens in gases and water. It is not possible in solid. Okay, so if you're talking about solid to water, the heat transfer from solid to water, just like the heating coil to the water. That is true conduction. Okay, because the region of water that is close to the coil is receiving the heat from the coil. So that is true conduction. And then when the heat goes to water, it's only the region of water surrounding the heating coil. When you want to distribute to all parts of the water, then it's true convection. So two modes at the same time. Conduction first, and then convection comes after. Convection. Okay, so convection is from water to all parts of the water. Similar to a cooking pot. Okay, you put it over the flame. First, you start from where? The flame heats up the pot at the bottom. That is true radiation. Okay, radiation. And then the bottom of the pot heat up the water through conduction. And then the water distribute all the heat to everywhere through convection. All three modes happen at the same time. Okay, next one. This one, right, the convection heat transfer, movement of particle is like just like the free electrons in conduction. Okay, the particle, they carry the energy and then they move, just like how the electron move from one place to another place. So the particle can also move, carrying the heat energy with it. Okay, next. Now we come to radiation. What is radiation? Okay. Radiation, of course, there are many, many types of radiation. Radiation is generally referring to the EM waves. Okay, what is EM? Electromagnetic waves. The transfer of heat through the electromagnetic waves. How many electromagnetic waves you have? The family, the big family, seven members of the family, right? Radio wave, UV, infrared, all that. All of them, they are radiation. Okay, so when you hear people say radiation, then is these seven. Of course, there are many more. There are two more actually. There are alpha and beta radiation, but this one we don't talk about this one here. Okay, this one is for the radioactive types of radiation, the danger type. So the thing is, all radiation, they carry a certain amount of heat, but the radiation that we talk about here, we focus on the infrared. Okay, infrared radiation. Which one is the infrared? Counting from the left, it is the third one. Okay, you have the radio wave, the first, second one, microwave, right? And then you have infrared, and then you come after that is light. All the seven waves, can we see it? We can only see light, right? We can only see light. But the one before light is infrared. Can we see infrared? We cannot see infrared, but we can detect it. Our skin can detect it as heat. So when you feel hot, then you're receiving infrared. Okay, you have receptors that detect infrared, even though you cannot see it. After light is UV. Can you detect UV? Can you see UV? You cannot see UV. Right? You cannot see UV, but you can feel it, but only after a certain period of time. Okay, you go to sunbathing, you go to sun tanning. The next day you get sunburn. The next day only you know you get sunburn. Okay, so there's a time delay. There's a time delay. The next day only you know, oh, I'm exposed to UV. Okay, so here again, we have a detector for UV. It's also your skin receptors, but there is a delay here. Every radiation, there's a way to detect it, but the only one that we can see is light. So I want to highlight this one, the infrared here. Infrared is known as the heat wave. The heat wave. Okay, so how heat transfer from one place to another place is through the emission of infrared. Okay, here, the sun heats up the car down the street through radiation. How far is the sun from the earth? A few million kilometers, right? And there's no air in between. There's vacuum in between, right? Through the vast distance, there's vacuum in between these two. There's no medium. There's no medium in between. Okay, so how the heat can reach the car is through EM waves. So it's through infrared, because infrared does not need medium to travel. So radiation is the transfer of heat via EM wave without needing a medium, without medium. Okay, it can reach like this. Similar to a campfire. If you stand near a campfire, that is also radiation. You stand near a candle, the heat that you feel, that is also radiation. Okay, you stand near a light bulb, that is also radiation. The heat that you feel from a candle, bulb, or the sun. They are all examples of radiations. Okay, now, when the sun heats up the object, what happens is that this car, right, the object, it is an absorber of the infrared. If you remember in the light chapter, whenever energy strikes, what happened? Rad, right? R-A-T. Light is an energy. It is a wave. When it strikes a medium, there's a reflection, absorption, and transmission. Similar to this one. Infrared is also an energy. It is also wave. So when it strikes an object, there's an absorption, reflection, transmission. Okay, so there's a certain amount of absorption. So the car will absorb the infrared. Okay, you take in the infrared and then it heats up. Since the sun is the one that giving out the infrared, right? So this one, we call it the emitter or the radiator. Radiator, emitter. What happens when the car absorbs the infrared? The temperature, first the temperature will rise. And then when the temperature rises, right, until it becomes higher than the surrounding temperature of the air, then it starts to radiate to the surrounding. Okay? When it absorbs the radiation from the sun, the temperature of the car rises. And then when the temperature of the car is higher than the surrounding, again, you have this difference in temperature, the car will start radiating. Now it is doing the job of radiating back the infrared to the surrounding air. So the infrared will come out to surrounding air. So now the car is a radiator. Is it still absorbing? Yes. Answer is yes. The car is absorbing from the sun and radiating to the surrounding at the same time. Does it absorb more or radiate more? Depending on the temperature. If the temperature is rising, then the absorption is more than the radiation. If the temperature is falling, then the radiation is more than the absorption. So any object, they can emit and they can absorb at the same time, depending on which one is greater. That defines whether it is heating or cooling. Understand? Okay. So in the night, when the sun is not there, then the object is only doing the job of radiating. There's no more absorption, there's no more sunlight. So in the night, it's only radiating the heat to the surrounding. That is the transfer of heat in the form of radiation. Okay, how do you prove that? Okay. Few things that affects the radiation. First is the surface temperature, the initial temperature of the surface. So if the surface is very hot, then it radiates quicker. Okay, if the surface is not as hot, then the radiation is slower. The surface temperature affects the rate of radiation. Second one is the surface color and texture. So dull and black objects, they are good radiator. Good radiator. Okay, take note of this. Objects that are good radiator, they are also good absorber. Good radiator, generally, they are also good absorber. So black color object, they absorb heat very fast, but they radiate heat also very, very fast. Okay, so why black color object is a very good absorber? Why does black color object absorb heat very fast? Not only black object absorb infrared very fast, it can even absorb light, you know, because it absorbs light, that is why it is black. Okay, so if you look at the spectrum, the EM wave spectrum, not only it is a good absorber of infrared, even light also it absorbs. That is why it appears black. No color is coming out. Right? So you see color is because the color is being reflected. It's like, for example, if you see green color, right? It's because of green color is being reflected to your eyes. If you see white color, it's like all the color is being reflected. If you see black, then no color is being reflected. No color is being reflected. So you see absence of color, that is black. Okay, so it absorbs infrared and also the visible spectrum, okay, the light here. So that is why black surface is a good absorber. Okay, so good radiator is generally a good absorber. Now, the third one that affects the radiation is surface area. So if you have common sense, like if you have more surface area exposed, then the radiation happens rapidly, okay? Higher surface area compared to smaller surface area. Okay, here we got two tubes filled with boiling water. Aluminium tubes filled with boiling water. One is covered with shiny surface. Okay, one is covered with a dark surface. Here we are doing an experiment to study the rate of radiation. Which one radiate quicker? Which one? After a certain period of time, you find that the boiling water with the dark black surface, the temperature drops faster. Okay, temperature of water with dull black surface decreases more rapidly. Okay, here it says matte black, not shiny, because shiny is a good reflector, not a good absorber. Shiny surface. Okay, it's like dull matte black surface. Matte black is like it doesn't reflect light, right? So when you see, it doesn't look shiny. So radiation is affected by all these three. Okay, so after a certain period of time, you find that the temperature here decreases rapidly compared to here. next one. Okay, a vacuum flask, the application of radiation. A vacuum flask is designed to keep liquid hot by reducing heat loss through all three types. So it uses the three modes of heat transfer to keep liquid warm. Now, here are the important features: stopper, trap air, vacuum, and silvery glass wall. Okay, first is the stopper. The lid. What does the lid do? Prevents the setup of convection current. How does it prevent the setup of convection current? Convection current is set up when there's a difference in the density, right? You have like warm air at the bottom, cold air at the top. Difference in density, then convection happens. So if you have the lid on, it's like it makes the air inside the same temperature, okay? The air inside here, and plus the volume is also very small. So it's very hard for convection current to set up, okay? Because the volume of air is very small here, and they almost have the same density, same temperature. Okay, so it's very hard for the convection current to set up if you have the stopper on. So this is to reduce the heat loss by convection. Okay, that's the first one. And then trap air. Now trap air, you see, it separates the lid with the water. Prevent the water from touching the lid. So that reduces heat loss by conduction. Okay, there's no contact, so no conduction happens here. And plus, air is a very good insulator of heat. Okay, why air is a good insulator of heat? Generally, gases they are good insulator because the particle, they are very far apart. If you think of solid, particle very close. So when one particle vibrate, the next one vibrate as well. So this transfer happens efficiently. If you talk about gases, the particle is very far away. One particle vibrates, it's very hard to reach. It's very hard to reach the second particle. Okay, so the transfer of heat becomes less efficient because of the spacing between molecules. They are very far apart. So that is why air is a good insulator of heat. Okay, so reduces the heat loss by conduction. Then we have vacuum. Okay, so often you see this is what we call the double glazed window. It's like double wall, and then between the walls is vacuum. Okay, people use it like in the construction of buildings, windows. Sometimes they use double glass wall. So it's like in the middle is vacuum. This is to prevent the heat from transmitting. Okay, how does it work? See, because middle is vacuum, so radiation can get through only. Convection and conduction is not possible. It's not possible for it to cross the bridge from one wall to the second one because the middle is vacuum. Convection and conduction, they need particles. Okay, so it reduces heat loss by conduction and convection. But can it reduce radiation? It cannot reduce radiation. Radiation can still go through, But that is why the wall is painted, okay, it's coated a silvery glass. Silvery glass wall, we make it shiny surface and smooth surface. Because shiny and smooth, they are very good reflector. Okay, reflector. Silvery wall reflects radiant heat back. What is radiant heat? Radiant heat is infrared. Okay, it's talking about infrared. The same thing. Radiant heat is the infrared. So silvery wall reflects radiant heat back into the liquid. So the radiation from the liquid tries to get out. When it hit the silver surface, the smooth surface, it is a good reflector. It reflects it back into the liquid. Okay, so keeping the liquid warm. All of this, it's like one whole integrated part. They complement each other. All three modes are involved in keeping the liquid inside warm. Yep, so that is for the vacuum flask. Okay, conductors and insulators. Here you have a table showing the thermal conductivity of a few substances. Highest, silver. Okay, now the thing is about thermal conductivity, the higher it is, the better is the conductor. Okay, the better it becomes, the better it behaves as a conductor. So high thermal conductivity means good conductor. Okay, now a good conductor, not only it allows heat to transfer easily, it also lose heat more quickly. Okay, so it absorbs heat quickly, it loses heat more quickly. Good conductor. Okay, so here you have a thermal conductivity of few materials. Look at water and air. They are way down here, water, and then we have air here. Air is the lowest one, meaning that it is a very good insulator. Okay, water is also a very good insulator because you see the specific heat capacity, 4200 joule kg degree minus 1. Okay, the 1 degree can keep many heat energy. Okay, you can store many heat energy. A huge amount of heat energy can store. So that makes water become a very good insulator. And usually water, they use it for what? For the cooling in the engine. The car engine, okay? Inside the car engine, there's this piston, right? Where combustion happens. So they use water to cool all this working of the engines. Because water, they can absorb a lot of heat. It has very high specific heat capacity. If something that has a low specific heat capacity, right, you use it for insulator, then it absorbs a little bit of heat, then the temperature rises until the boiling point and it boils already. Okay, we don't want that to happen. So water is able to absorb a lot of heat without much increase in the temperature. And then we have a much better insulator down here. Air, polystyrene, wood, plastic, they're all good insulators. And conductors are metals, stainless steel, silver. Stainless steel used in the making of the cutlery, okay, cooking pots, all that. Okay, standard glass, concrete. Now here, air is a very good insulator because of the state of matter. Gases, usually they are better than liquids. Okay, now what is the difference between thermal conductivity and specific heat capacity? Are they the same? Thermal conductivity is a measure of how good is a substance pass on the heat. Okay, if you think about conducting heat, right? Meaning that whether the heat can flow easily or not. It's like the ability of the material to pass on the heat to the next atom, right? So if like you have one atom like this, right? The structure, So you hit one end, we hit here. The ability of this atom to pass the heat on to the next one, and onto the next one, onto the next one, onto the next one. That is thermal conductivity. Okay? How good they pass on the heat. But specific heat capacity is different. Huh? Specific heat capacity is, it talks about the temperature. Okay, it talks about the temperature. So how much energy used to raise the temperature by 1 degree. So how do you raise the temperature of the substance? It has to be the average kinetic energy to increase. Only the temperature will increase. You see the difference. Thermal conductivity is a measure of how well you pass the heat. But specific heat capacity is a measure of how many energy you need to increase the temperature. Okay, how well you pass the heat doesn't mean that the temperature must increase, because temperature is a measure of average kinetic energy. So only if you have every single atom vibrate faster, it push up the average value, then the temperature will rise. Okay, they are kind of related, but they are not the same. Okay, so I just want to highlight a bit of the difference here. But generally they are very closely related. But one is the measure of the passing of heat. Another one is the measure of the increasing in temperature. Okay, how fast is the increase in temperature? And to increase the temperature, you need to increase the average value. Average value. It is easier to increase the temperature of a cup of coffee than to increase the temperature of the entire ocean, because it's easier to push up the average kinetic energy of the particle in the cup of coffee, because you have less particle than the particle in the ocean. So it's way harder. You need a lot more energy to increase the average kinetic energy of the ocean. Okay, so which is why they said if the ocean temperature rises by 1 degree, that is actually a lot. Very, very huge amount of energy. If the ocean rises by 1-2 degree, that is a lot of energy, because you need to push. If the ocean temperature rises by 1 degree, you are like pushing the average kinetic energy of the every single particle in the ocean. Okay, you're pushing the average value up. Okay, so these are the conductors and insulators. Users, we don't need to go through, all right? We can just read through the users, all that. Okay. Okay, I'm going to give you a break. We take 3 minutes and then we continue. Okay, so we come back at 5:38. 5:38, we continue the next part. Huh? Okay. Okay, we continue to the next part. The difference between boiling and evaporation. Okay, so first, let's talk about when does it happen. Boiling happens at boiling point. So if you're talking about pure water, 100 degree Celsius. What about evaporation? Evaporation happens at all temperatures. Okay, that's the first difference. It occurs at all temperatures. Then we talk about the difference in terms of the nature. Why does boiling occurs? Why does boiling occurs? Okay, let's say I draw a beaker here. Say that we have a liquid. Think about the liquid as particles arranged in layers. Okay, we have the first layer. We have a second layer deep down. And then we go deeper and deeper like this. Okay, so when I heat the water, the particle is going to gain energy. Okay, it's going to gain energy. And what happened here? Every single particle, they get energy, and even the particle at the bottom, this particle here, it can also escape because they are all receiving the same amount of energy, right? The particle at bottom here or the particle up here can jump out. This particle also can jump out. Any particle can jump out. So boiling occurs at every point in the liquid. Okay, it occurs at one temperature, 100 degrees Celsius, and it occurs at every point in the liquid. If you compare to evaporation without heating it, the particle, okay, one thing you have to understand is that particle in a medium, not every single particle, they have the same kinetic energy. Some vibrate faster and some vibrate slower. Only the faster one can escape. And usually you find these particles at the first layer, the one that is closest to the surface. The one that is buried deep down, okay, they cannot escape. Only the one close at the surface. This particle, they generally have higher kinetic energy. They can, from time to time, they can jump out from the surface of water and escape into the atmosphere. So that's evaporation. Okay, so evaporation happens at the surface and boiling happens at every point. That is the second difference between boiling and evaporation. Okay, and also you can say evaporation is a slow process, boiling is a quick process. Right. So each particle having different amount of kinetic energy. Only the faster one can rise up. Now, and also boiling happens when the pressure reaches the atmospheric pressure. Okay, so also this is one thing to take note. So when I heat a substance, why boiling occurs is because when the particle don't just like jump out like that. They don't just like jump out like that because there's something that preventing the particle from jumping out. What is it? It is the pressure that is preventing the particle from coming out. What pressure? Atmospheric pressure. Okay, atmospheric pressure. Atmospheric pressure is due to the weight of the atmosphere. Due to weight of the atmosphere. Anything has weight. Even water has weight. So we have water pressure, right? As you go deeper down into the sea, the ocean, you find it difficult to breathe. That is also because of the pressure. It's come from the weight of the liquid. Same apply for gases. The atmosphere has a weight, but we don't really feel it, right? Okay, we don't really feel it. Okay, there's a reason why we don't feel it, but that one we save it for the pressure part. Okay, how come we don't feel the weight of the atmosphere? Okay, I'll talk about that one more in the next part. So the point is here, atmospheric pressure is due to the weight of the atmosphere, so it is preventing the particle from escaping. So what the particle need to do to overcome this atmospheric pressure, they need to build an army, something like that. Okay, they need to build a pressure as well. Okay, we say like they build an army. Every particle that come up from the surface, they are temporarily stuck at the surface of the liquid. Okay, so it's like particle come out, they gather around at the surface of the liquid, just above the surface. Okay, it's like very, very thin layer. Of course, we cannot see lah. So a very thin layer, they gather there. They are building an army. They are building a pressure that we call the vapor pressure. Okay, you may have come across this term, vapor pressure. So all these fast-moving particles, like steam, hot steam, they build up the vapor pressure. And this vapor pressure, if it's smaller than the atmospheric pressure, then still they cannot escape. Only when the vapor pressure is equal, that is when the boiling starts. Then particle can start to leave the surface and go in air. Okay, so that is what happened at 100 degree Celsius boiling point. Okay, that is for pure water. So does the atmospheric pressure affect boiling? Yes, it affects boiling. So boiling point of water, 100 degree, it is only at standard atmospheric pressure. If you go to the top of the mountain, where the pressure is different, because at the top of the mountain, at high altitude, there's less air, right? Less air means less weight. Less weight means less pressure. So the atmospheric pressure up there is less than the atmospheric pressure at our ground level. So the boiling point of water is different up there. Okay, so the atmospheric pressure will affect. Okay, let's go to the next slide, because this one is supposed to be the next slide one. Okay, so here is you take note of the difference between the boiling and evaporation. Okay, next one is here. Okay, I go to this slide first. Okay, this one is just what I just talked about. For liquid to boil, the vapor pressure of the liquid must equal that of the atmospheric, but must equal to that atmospheric pressure. Okay, so the atmospheric pressure is greater than the vapor pressure, so the water will not boil, and it's here. The atmospheric pressure is equal to the vapor pressure, the water starts to boil. Okay? Only when they achieve an equilibrium in the pressure, the particle can come out. How does the atmospheric pressure affect the boiling point? when the atmospheric pressure, ATM, decreases, what happened to the boiling point? And just think about logically, right? So if the atmospheric pressure decreases, meaning that this force here is now less. This force here is now less. Okay, so it makes the water molecules easier to overcome because now the force is less, right? So the water molecules here, when they try to overcome the atmospheric pressure, is now easier, meaning that the boiling point will decrease. Okay, atmospheric pressure decrease, boiling point will decrease. So boiling point of water at, if you bring it to the top of the Mount Everest, okay, top of the Mount Everest where the pressure is relatively low, then the boiling point is at around 68 degrees Celsius. Standard atmospheric pressure is 100 degrees Celsius. You bring it to the top of Mount Everest, it drops to 68. So you boil water up there, it's only until 68 degrees Celsius. You touch it, it's not even that hot. It's not even that hot. It's already started boiling. Okay, already started turning into gas. If you wait until 100, maybe the whole pot already gone. No more water here. Okay, so that is the relationship between boiling and the atmospheric pressure. Same for evaporation, the same effect on evaporation. Okay, now we look at the things that affect evaporation. This one, oops. Okay, factors affecting the rate of evaporation. Number one, an increase in the temperature of the liquid or the temperature of the surroundings. Okay, so any increase in the temperature of the liquid will speed up the evaporation simply because more particles, they have enough kinetic energy. B, an increase in the exposed surface area. So exposed surface area means like you have a container that is like flat, and then you have a, let's say you have a cylinder. Assuming that they have the same volume of V1, V2, V1 equals to V2. Which one evaporate faster? Of course, the first one, because more exposed surface, more room for the particle to get out. This one has less room. Okay, this one is more particles are at the surface. Okay, C. A decrease in the humidity. What is humidity? Humidity is like how wet is the air, surrounding air. Okay, how wet is the air? So if the air is wet, does it speed up evaporation or slow down? If the air surrounding is wet, then it slows down the evaporation. Okay, why? Because if the air is wet, that means you have like droplets of molecules, right? Okay, you have like water droplets, that you have moisture. Okay, all this moisture, right? The particle has low energy. They have low energy compared to dry air. This particle, they have low energy, meaning that they, as the particle try to escape, then maybe this nearby particle which has low energy will drop down, it will drop back into the liquid. Okay, all these water droplets, they have a tendency to drop and come back to the liquid like this. Okay, so it's like you have particle trying to escape, trying to evaporate, but then the surrounding moisture, okay, the particle, they come back to the liquid. So it slows down the evaporation process. That is different if the surrounding is dry. The surrounding air is dry, then what happens is that once the molecule escape, it will not come back. It will not come back. Yes. Okay. This one done. Next one, D. The pressure of a drop or wind blowing over the surface. Now, it's the same reason. You can relate C and D. If you got wind blow, then it carries all this particle away. Okay, all this particle. All these particles that are stuck above the surface, they have a tendency to come back into the liquid. So if you have wind blowing, you carry them away, preventing them from dropping inside the liquid. So it speeds up the evaporation. Okay, so that is the wind movement. And E, last one, a decrease in the pressure acting on the surface of the liquid. Okay, so this is what we discussed about the atmospheric pressure. Okay, so if you have lower pressure, then particle easier they can escape. Right. Let me go to the next one. Okay, so this one we just went through. Why the boiling point of a liquid is affected by the atmospheric pressure. The atmosphere contains molecules that are in constant motion, and they exert a downward force on the surface. The higher the air pressure, the harder it is for the liquid to evaporate. And therefore, the boiling point of a solvent or liquid is affected by the pressure, and the boiling point is raised. A liquid in a high pressure environment boils at higher temperature. And when placed in a lower pressure environment, it boils at lower temperature. Okay, next one. Okay, here we talk about the melting point. Just now we talk about boiling, right? How about melting? How does the pressure affect the melting point? The pressure and the impurities. All right, good. Okay, point number one. Liquids usually have higher volume than their solid counterparts, except for ice and water. Now, here's a question. If I increase the atmospheric pressure, what happens to the melting point? Not boiling point, is the melting point of ice. Melting point of ice. What happened to the melting point of ice if I increase the atmospheric pressure? First thing you have to understand is that in general, for most substances, the liquid form is usually have a higher volume than the solid form. We are talking about the same substance. Okay, for any one substance, the liquid form have a higher volume than the solid form. Because liquid, simply because the spacing is further, right? Solid, they have tighter arrangement. So the liquid they are further out. So the liquid usually have a higher volume than their solid counterparts. But except for ice and water, okay, except for ice and water, because ice and water, they special a bit. What happened to ice and water? Ice is solid, right? Solid. So ice actually has a greater volume than water. This one you learn in your chemistry, right? So water is liquid, less volume. Why? It's because of the structure. When water freezes into ice, there's a structural change. Okay, they arrange themselves in this crystal structure where the structure takes more volume. Okay, so when water turns into ice, actually it expands, the volume becomes bigger. That is not the case for most substances. Okay, so only ice and water. So meaning that for most substances, the melting point increases if I increase the pressure. You see, if I increase the pressure, you can think of it like this. If any solid want to change to liquid, since for most substances, liquid has a higher volume, right? And solid is lower volume. When they want to change from solid to liquid, meaning that there will be an increase in volume. They need to take up more volume to change to liquid, right? For most substance, okay? When they want to melt, they need to take more volume. But if the surrounding pressure is very high, then it will compress it. It's kind of like pressing them, preventing them from expanding. Because if they want to melt, they need to expand. They need to take more volume. So if the pressure is very high, then they cannot expand. So this will increase the melting point of the solid substance. Because if they find it very hard to expand, they need to take more heat. They need to take more energy, and you need to heat it longer. So melting point will increase. Understand? Okay, so melting point will increase if you increase the pressure. Okay, if they ask you to explain, then you know. Why? Because when they expand, they need more volume, and the pressure is preventing them. Okay, so melting point is higher. Now, that is for most substance, but not except for water. Water is different. Again, water is different, meaning that if you increase the pressure, what happened to ice? The melting point of ice. Is the melting point of ice increase? The answer is it decreases. Okay, why? Is because when ice turn to water, which one has a greater volume? Ice has greater volume, right? Water has less volume. So when ice change to water, it actually take less volume. Okay, take less volume. And if you increase the pressure, think of it like you compressed it. Okay, you compressed it. It makes it much easier to change into water, because it actually takes less volume to change to water, right? So much easier to change to water. That means that the melting point will decrease. The melting point will decrease. Okay, so here we said that the melting point of ice decreases with increase in pressure. Remember, this one is for ice and water. Okay, point number 3. This is for melting point, and the previous one is for boiling point. So meaning that sometimes you've seen this term, like they said, force melt. Okay, they can force melt something. They can force melt something using pressure. Because if you have high pressure, without much heat energy, you can still melt it. It's because of this reason. Okay, so high pressure lower down the melting point, so we can force melt even before it reaches the melting point. Okay, let's say the ice melting point is 0, right? 0. If I have high pressure, I use high pressure to melt the ice, I can melt it at, let's say, -2. Much earlier. Okay, even before it reaches 0, it started melting. Okay, with high pressure, I can do that. This is called force melt. Force melt. It happened where? Where does it happen? It happened in ice skating. Okay, ice skating. If you've seen people who skate, they know this. The skating shoes, actually they have very sharp, like pointed thing underneath is to, when it stand on the snow, it exerts a very high pressure on the snow. Okay, so what this thing does is that it force melt the snow, okay, so that it becomes slippery. So the snow become like liquid, and then it makes them easier to skate. Okay, it's underneath their snowshoes. Okay, the snowshoes, it's like this pointed thing. They can force melt when they step on the snow, they force melt it, and then it creates a layer of liquid that makes them easier to slide, to skate. Okay, so this is one of the applications. They use high pressure to force melt. Right. Okay, the next one. Presence of impurities. Impurities like I can add salt. Okay, any other substances. Salt. If I add salt to ice, what happened to the melting point? So the thing is, salt, it weakens the bonding. It weakens the lattice. So ice added with salt melts again at lower temperature. So again, it decreases the melting point. It makes it melt easily. So these are a few things to take note lah. Effects of pressure impurities on melting point. Let me go to the next one. Okay, the last one. Refrigerator. Okay, the working of the refrigerator. Using the boiling, condensing, and evaporation concept. Okay, now how does it work? We just look at the simple working principle. Now, the things, before we look at how does it work, few things to know. You look at the bullet point at the bottom. When liquid evaporate, it absorbs heat. Okay, when liquid evaporate, it absorbs heat energy. Because if you want to go from, okay, something's wrong with my mouse cursor. Let me change with give me a second. Okay. So if you want to go from liquid to gas, then you need to absorb heat energy. Absorb heat energy. So whenever liquid evaporates, it absorbs heat. This is the first thing you need to know. So it's the same principle as if the moment you come out from the swimming pool, you feel very cold. Why? If you're in the swimming pool, you feel warm, right? So when you come out, you feel very cold. It's because the water evaporates on your skin. Okay, the water droplets on your skin. Okay, this is your skin. Actually, it takes the heat from your body. Okay, it takes the heat from your body and then it evaporates. The droplet turn into gas. So evaporation absorbs heat energy. Okay, it absorbs heat energy from your body, and that makes you feel cool. There's this sensation of cooling. Huh? Okay, second thing is when gases condense, it releases heat. So if I go from gas back to liquid, it needs to release heat into the surrounding. Okay. Point number 3. If you compress gas into less volume, then the gas becomes hotter. Okay, it's like you pump the air in the bicycle tire. Okay, you feel that there's the air will become hotter inside, or a car tire. Okay, you pump the car tire because you're forcing air in volume 1 into smaller volume. Compress means you pressed it lah. Okay, you pressed it from larger volume into smaller volume so that the particle, they take less space. The particle does not change. The amount of particle is the same. Okay, you're forcing them like this. So there'll be more heat. Sorry, not more heat. The temperature will rise. The temperature will rise. So if you compress gas, then it becomes hotter. Or it's like the airplane engine. You know the engine, they have a lot of this compressor, right? They have a lot of blades. One blade, behind one blade, there's another blade. Behind it, there's another blade. There's a few layers of blade. So this blade, they spin, right? They spin. So when they spin, they compress the air particles. Okay, they spin, they compress the air particles. Okay, last one is expand gas into more volume. Now, when you allow gas to expand into more volume, so you take the reverse, the gas will cool down. Okay, the gas will cool down. Okay, these are the few things that you need to know before we talk about the working of the refrigerator. Okay, now let's see, how does it work? A few components, a few components of the refrigerator. We have the E, this is the expansion valve, this point E here. And then we have compression pump at the bottom. This is to compress air. And we have the cooling tube. This cooling tube is, you find it outside behind the refrigerator, the black coils, okay, outside the refrigerator. And then you have also another tube that is found inside the refrigerator. Okay, so this is outside and this is inside, the one on top here, the ice box. Okay, inside the ice box you have another tube. Okay, now let's see how it works. Start from number 1. See here, when the compression pump is switched on, the refrigerant, okay, refrigerant is like a type of gas. In the refrigerator, sometimes it becomes gas, it becomes liquid. Okay, so we call it refrigerant. Refrigerant expand into the tube surrounding the ice box through valve E. So first we allow it to expand. What happened when it expands? When it expands, it cools down, right? So here it enters here as liquid. Initially it is liquid. It's liquid. The liquid that has been cooled down through the expansion. Okay, when it goes through the expansion valve. The refrigerant is in the form of liquid here. Now, this liquid is then passed through the tube in the ice box. It's inside the refrigerator. What happened is that inside the tube, the refrigerant evaporates rapidly. Why does it evaporate? Because it is taking the heat from the air inside the refrigerator. The air inside the refrigerator, initially it is warm air that is coming from the food that you put in. Okay, because the food that you put in, it releases warm air, and this warm air, the heat energy flow from the warm air to the liquid, the refrigerant liquid. So the liquid evaporate. Okay, so the refrigerant evaporate, absorbing. As it evaporate, what happens when it evaporate? It absorbs heat, right? So absorbing the latent heat from the ice box, from the air surrounding the ice box. Okay, so as it absorbs the heat, the air surrounding the ice box becomes cold. Okay, then you get cold air inside the refrigerator. Now, when they absorb heat, right, it evaporates. So meaning that coming out from this tube, down, you see this arrow down, coming out from this tube, it become air already. Now it is air because it already evaporate. This refrigerant is in the form of air. And what happened? This cold air is denser than the surrounding air. Okay, this air, it is talking about the air inside the refrigerator, not the refrigerant in the tube. This is talking about the air inside the refrigerator. So the cold air is denser than the surrounding air. It falls to the bottom of the refrigerator and causes warm air to rise again to the top and be cool. Okay. Number 4, the heated refrigerant. Okay, this is the one that I'm talking about. Okay, the heated air that passes down from the top. Okay, inside the tube, move to the compression pump down here. What happened here? They compress the air. They compress the hot air, and when they compress, temperature increase and pressure will increase. Okay, they compress, temperature increase and pressure increase, and after the compression, they are channeled through the cooling coil. This is at the back of the refrigerator. Okay, so when they go through this cooling coil, right, they release heat to the surrounding. Okay? Because you see, the compressor increase the temperature so that the heat transfer is from the coil to the surrounding and not from the surrounding to the coil. Remember, heat flow from high temperature to low temperature. Okay, so I compress the air so that it becomes hot. When it flows through the cooling coil, it releases the heat to the cooler air in the surrounding. So I can throw the heat out. Okay, I can throw the heat out. And then when it releases heat, the gas, what happened when the gas release heat? Point number 2, when gases condense, it release heat. So these gas will condense back into liquid and pass through the expansion valve again, and the whole process repeat. Okay, the whole process repeats. Point number 5. As the warm compressed refrigerant flows through the cooling tubes on the outside of the refrigerator, it releases heat and then condenses back to liquid. Energy is dissipated to the surrounding through the cooling fins. The cool refrigerant then flows through valve E again, and the cycle is repeated. Understand? Okay, so how does the refrigerator cool the air inside? As simple as it sounds, it just uses condensation and evaporation. The principle behind it is using condensation and evaporation, because when liquid evaporate, it absorbs heat, and when gas condense, it releases heat. So basically, it absorbs heat from the food inside and then throw it out. Release, absorb heat, throw it out. Absorb heat, throw it out. So we are not destroying the heat, we are just transferring, moving the heat from one place to another place. That is the same for the aircon. Okay, it's the same for the aircon. It takes the heat from inside, throw it out. So if you go to the radiator at the back of your house, the aircon radiator, then you feel very hot there. Okay, and they can also do the reverse. They can take the heat from outside, put it inside. That becomes a heater. So we are just having a device that transfer the heat from one place to another place. So cooling is just the movement of heat. You're moving it from one place to another place. Okay, so if you move from place A to place B, then to place A, they experience cooling. Place B, they experience heating.